One, welcome back to Random Matrix Theory. Today we'll learn about something called Wigner's Surmise. And you'll see why I have highlighted the word surmise. So let's go into history a bit. So in the 1950s, Wigner was, so it's the story of Wigner. So in 1950s, Wigner was interested in energy spectrum of heavy nuclei. Let's say thorium and America's favorite nuclei, uranium. So these are very complicated nuclei. That is, they have different energy levels. These are very heavy nuclei. It's not as simple like the hydrogen atom. It's a very complicated nuclei. So he was interested in studying the energy spectrum. That is, if you know a bit of quantum mechanics, you know that energy levels are spaced. That is, they're discretized. They have different energy levels. Even if you don't know, just say there are different spectrum of energies. So they're discrete spectrum of energies. So energy levels basically mean electrons having different energy. So they're in different levels of energy. If you know high school chemistry, if you remember, they sit in different energy levels. So he was studying those things. So he studied the spacing, this spacing between energy levels. Let's say spacing S. This is how he came up basically with the idea of random matrices, but we'll go into that later. Let's study this example a bit. So if this values were uncorrelated numbers, these values, the variable S would be governed by something called, so let's first write it. If uncorrelated, they would be governed by something called Poisson distribution. So note, this is a very large system. That's why we need a distribution. It's a heavy nuclei. They have various level of energies. So we need a distribution to describe the probability. So if they are uncorrelated, they would have they would follow a Poisson distribution. They would be governed by a Poisson distribution, and their probability density would be, let's say, like this, something from the Poisson distribution. Right. So this was the original idea, because energy levels are spaced, and if they are uncorrelated, that is, the spacing is uncorrelated, they would be governed by the Poisson distribution, and the probability density would be given by this. But experimentally, we observed something very different. So experimentally, very different. And they are approximated by something called as the headline of the topic, Wigner's Surmise. As far as I know, the word surmise means something that you come up with without a proof, and Wigner came up with this idea just randomly out of his head with sheer brilliance, but no mathematically rigorous proof. So here's how the Wigner surmise looks. It's like C beta, where beta is any parameter squared, beta is any parameter, and beta belongs to 1 to 4, and we'll study these betas. They are part of a group called the beta matrix models. We'll study them, but let's first see this. So if you plot the graph, let's say you have PS here and S here, the spacing distribution, Poisson distribution, follows something like this, and I will try to draw it correctly. Yeah, something like this. This is the beta equal to 1. This person is beta equal to 2, and this is a beta equal to 4 scenario. And this is exactly followed by the Wigner surmise. That is, you can explain different betas correspond to different symmetries of the nuclei, but that is not important. So beta equal to 1, 2, 4 are due to different symmetries, but what Wigner did is with this graph, he correctly explained the energy spacing. And we'll see this now, why it's relevant to our scenario. So Wigner surmise, why is it important to our random matrix scenario? Because it's a very good approximation of the large size of the probability density for the distance between consecutive eigenvalues of a random matrix. So hold on to that thought. What does this mean? So the Wigner surmise that we saw here, I'm claiming that, which we'll see an example in a bit, I'm claiming that it's a very good approximation of the large size of the probability density for the distance between consecutive eigenvalues of a random matrix. You remember if I told you that the eigenvalues of a random matrix, they change because they're random matrices, the entries are changing, there will be different eigenvalues for different realization of the matrix. So if you have different eigenvalues, so the spacing will also change. So eigenvalue is also a part of a separate distribution, right? And what they mean by distance between consecutive eigenvalues is that, let's say if you have a distance like this, where considering S2 is greater, lambda 2 is greater than lambda 1, this spacing is described very well by the Wigner surmise. And we'll see an example in a bit. But first, let's see what is the usefulness of this. So remember, density is universal in the sense that when you will be doing matrix integrals, you will see that they don't depend on measure of the random matrix integral, but only on the choice of matrix ensemble. We'll see this in the next video, these two things. What is a measure? Measure is just the integration this is called the measure of integration if you're dealing with something like this. So they don't depend on the measure, but depends on the matrix ensemble we are considering. That is, with different betas that I mentioned in the Wigner surmise, they are basically different ensembles. For example, beta equal to 1 is a real symmetric matrix, corresponds to a real symmetric. Beta equal to 2 gives us complex Hermitian, that is complex Hermitian matrix where we randomly pick the values of the elements. And beta equal to 4 is complex quaternion. If you know what quaternions are, it's just generalization of complex numbers. We'll study these two in exclusive detail, but we'll throughout the course we'll almost avoid this. Nevertheless, the important thing to notice is that the Wigner surmise is a very good approximation of the distance between consecutive eigenvalues, not the distribution of eigenvalues. Because if you remember the eigenvalue distribution, we saw a glimpse of it. So large size of eigenvalues, if you remember from the last video, were approximated by Wigner semicircle law. If I'm gonna write it, it looks something like this, with less than equal to 2 or 0. So if you draw a graph, it's something like this: minus 2, 2, and you have x. So this is the eigenvalue distribution. That is, the eigenvalue distributions are governed by the Wigner semicircle law. This is the eigenvalue distribution. But when you're talking about the distance, probability density for the distance between eigenvalues, these two are very different things. They follow the Wigner surmise. Okay, now that we have talked a lot about Wigner surmise and the Wigner semicircle law, so it's time to see Wigner in action. That is, we'll see an example of how the Wigner surmise helps us go around. So example. So consider the 2 cross 2 matrix that is symmetric and real. That is, it's the matrix W. So it looks something like this. And as I told you, we are dealing with a random matrix. These elements are all random variables. Okay, so let's say we pick the elements x1 and x2, the diagonal elements, from a Gaussian ensemble with mean 0 and standard deviation 1, variance 1. If you remember how we defined how this is a notation of Gaussian distribution. And x3, let's say it comes from like this. So important question is asked, why is it half of it? We'll try to answer that through by the end of the course. But this is one of the interesting things about this matrix. So the question is, what is the probability density function of the spacing between the eigenvalues? Again, remember the eigenvalues, as I keep on repeating, the eigenvalues themselves are random variables, because again, different matrices have different eigenvalues and we are picking the elements from a distribution. So important question is, the question we will try to solve in this problem is, what is the probability distribution function, say PS, of the spacing, say S equal lambda 2 minus lambda 1 between its eigenvalues where lambda 2 is greater than lambda 1. Okay, let's try to answer it. As I keep on saying, I'll just write it for you. So Now, since we are talking about the eigenvalues, let's the only tool we have of only way of proceeding forward is using something called the characteristic equation. If you remember this, it's just the polynomial equation involving the eigenvalues. So you can write the characteristic equation like this: determinant of w equal to 0. It's stands for trace. It's determinant. So if I plug in the values of trace and determinant, lambda plus x1 x2 minus, and by a little algebra you will see that you'll get two values and they will be like this: plus minus square root of x1 plus 4. Okay, so the spacing s would be, we define the spacing s to be lambda 2 minus lambda 1. So the spacing s would be square root of x1 minus x2 squared plus 4x3 squared. Okay, now let's try to construct. Let's try to construct the spacing probability distribution. Okay, before we start, note that all of the three variables involved here, that is x1, x2 and x3, they're picked from a Gaussian ensemble or a Gaussian distribution, that is with of course with different mean and variance. So hold on to that thought. Let me write how the distribution of PS of the spacing turns out to be. So if you remember dx1, you have a square root of 2 pi factor. dx2, they're all picked from this person, and this person is picked from 0 and 1. This person is picked from 0 and half. So if this person is picked from 0 and half, you will have a square root of pi. If you remember, it's 2. In the Gaussian distribution, you had 1 over sigma of 2 pi, square root of 2 pi. So there's that. And so here we have square root of pi. And since we're dealing with Gaussian distributions with mean 0 and variance 1, it's just x1 squared exponential minus half x2 squared exponential minus x cubed squared. And we enforce something called the delta function. Why do we enforce the delta function? Because we want our spacing to be like this, or the spacing function s to be like this. Let's first talk a little bit of what a delta function is. If you remember, a delta function is something like this. If you have a delta function, it's just, yeah, it gives you the value where it's translated. And so the delta function ensures the spacing. So delta function ensures the spacing s equals square root of x1 minus x2 plus 4x cubed, sorry, 4x3 squared. So the delta function ensures that our integration has this following constraint, which we found out from here. right? So this is how we constructed our probability distribution function. Okay. So this expression PS gives us the probability distribution function of three random variables, x1, x2, x3, given the joint distribution of three random variables. So we have so this probability density distribution function is basically a function of three random variables, but we want everything in terms of S. That is the spacing between eigenvalues. So how do we do that? We do it by transforming everything into S. So we need a change of variables here. Change of variables. So we need a change of variables and we turn it into an integration involving only S. So how do we change it? Let's say we move to polar coordinates or spherical coordinates to be more precise. Sine theta. So we define three new coordinates, r, theta, and psi. There's that. And let's say x1 would be r cos theta plus psi over 2. x2 is psi minus r cos theta over 2. x3 would then be r sine theta over 2. So since we are doing a change of variables, we have to find the Jacobian to do things correctly, and it's of course your job to find the Jacobian. And when you find it, you'll see that if you work the Jacobian out explicitly for this case, you'll see that the Jacobian turns out to be, this is your homework. This turns out to be like this. Now let's enforce the change of variables. This homework will of course appear in your problem sheet 3. So back to our integration. 3 over 2 integration. Its r has 0 to infinity limits. If we enforce this, s minus delta function is just s minus r 2 pi 0 d theta. So let's move to the next line. So we have exponential. Let's give second bracket first. Minus half r cos theta plus psi over 2 squared plus minus r theta plus psi over 2 squared plus r square sine squared theta over 2. So again, you will be doing this integral. You will be doing the integral as homework. So if you do the integral, it's your homework. I'll give them in problem sheet 3. The probability distribution for the spacing turn out to be something like this. Now the important question is, it's your job to compare with the Wigner surmise. You'll see that with some values of beta and alpha, they're very well approximated by Wigner surmise. It's very similar. So the remarkable result, please note that we have picked the x1 and x2 randomly from a distribution. These are random variables. It's very hard to realize this, but our matrices are constantly changing values, and thus their eigenvalues are changing, and energy distance between or difference between the eigenvalues are changing. So everything is changing, and in this changing scenario, what Wigner's remarkable result does is the eigenvalue. It predicts the eigenvalue distribution perfectly. So it's sheer brilliance, and without any rigorous proof, he showed that. So you might point out that our case was pretty simple, as the variance of diagonal cases equal to half of diagonals. Also, we were dealing with a pretty simple mean and variance. You might point that out, but try redoing this with different variance and you'll see the Wigner Surmise holds. If you know a bit of Gaussian distribution, you know you can turn a lot of things into a Gaussian distribution with mean 0 and variance 1. But even if you don't know that, you'll see that the Wigner Surmise holds. So this was the result of Wigner, and we learned in this video we'll learn about how the eigenvalues are spaced. That is, even the eigenvalues are random variables and they follow a distribution which is the Wigner Surmise. And this is the important result of this video. Thank you.